Hello, we present VIRDO++, Real-World Visuo-Tactile Dynamics and Perception of Deformable Objects. Deformable objects are ubiquitous in our day-to-day lives. The clothes we wear, the food we eat, many of the tools we use in our own biology are just a few examples. VIRDO++ is built on a recent work, VIRDO, which provides a framework for visual-tactile state estimation using implicit neural representation. This approach offers a number of advantages, including computation speed, state estimation using partial information, direct integration with raw sensory feedback, and learning correspondence without supervision. However, it does not address deformation predictions due to the lack of a dynamics model. Also, it is not directly applicable to real-world robotic settings due to the need for the contact patch, which is typically impractical to measure in real-world robotic settings. In this study, we address two major limitations of VIRDO via introducing action condition dynamics in contact code. Based on this, we show how these extensions enable real-world tasks and demonstrate our approach on spatula and chain manipulation. We assume a high occlusion manipulation scenario using deformable objects. We can obtain reaction wrench at the wrist and partial point cloud. Using VIRDO++, we can perform a state estimation in a fast and highly accurate manner using the partial information. Given the desired action, which is a Cartesian displacement of end effector, our model can predict the reaction wrench at the next time step. Then, model predicts 3D geometry conditioned on the wrench prediction. Here, we visualize the predicted geometries overlaid with the ground truth 3D and 2D images. One of the main contributions of VIRDO++ is to represent deformable object dynamics using an action model. The action model produces the next step's boundary conditions, where the inputs are the current latent state and the action. An object's latent state is computed from the reaction wrench, contact code, and end effector pose. Previous work uses ground truth contact patches, which required access to this privileged information. In this work, we proposed the learnable contact code as an input. The contact code unlocks the capability to run VIRDO++ in real world and even represent additional useful information beyond just the contact location, such as the histories of deformations. Here the latent state zt and alpha are learned to represent 3D geometry or sign distance function. With our learned dynamics, we propose a state estimation algorithm. The first step of this algorithm is to refine the latent state using sensor measurement via ADAM optimization steps. The second step is to resampling particles in order to maintain a belief distribution over a sequence of deformed object shape. Each particle represents one latent code, which corresponds to one specific deformed geometry. Finally, we roll out the dynamics to predict next step's boundary conditions. This predictions provides a great initial value for the next refined step. In this work, we thoroughly analyzed VIRDO++ and its inference algorithm in real robotics applications with two different types of objects, spatula and bi-chain. For training our model, we use training dataset, where it has 4 training objects. For each spatula in the training dataset, there are 25 trained trajectories, where each trajectory has 24 sequential observations. We evaluate our model using test and generalization dataset. Both dataset contains artificially generated occlusion at the tip of the spatula for 15% of the total length. Test dataset is about unseen trajectories of 4 objects, and generalization dataset contains 2 unseen spatulas, unseen trajectories. This is an example result of our model on test dataset. The predictions and state estimation results are shown in magenta, and they are almost perfectly overlaid with the ground truth colored in black. The geometry prediction tends to be less accurate because it is computed by rolling out learned dynamics using previous observation and action. State estimation uses the current measurement to update the prediction to match the current sensor measurement. As in the left panel, we highlight that state estimation uses a partial point cloud with artificial occlusion at the tip. This video shows more of our test results.
When scraping a table with a spatula, the robot must reason over the contact location to ensure the spatula is scraping properly at the desired region on the table. In this section, we performed extrinsic contact detection as a downstream task using the same dataset. In this figure, the table is indicated as yellow plane at z equals 0.
VIRDO++ can predict the line of contact at the next time step by rolling out the learned dynamics. Magenta spatulas are reconstructions from VIRDO++. When the robot moves, we can apply Bayesian filtering using partial point cloud and reaction range measurements. The Bayesian filtering increases the accuracy of contact location detection as the red lines get closer to the dotted blue lines, following the green arrow. Finally, we can repeat this process throughout the entire trajectory. Quantitatively, VIRDO++ can accurately detect contact locations with less than 8 mm of error on a flat table for the current and the following time step, regardless of occlusions. This is less than 4% of error in total length. Here we quantified the performance against ablations without contact code and rigid body assumptions. This illustrates the importance of contact code and reasoning over compliance. VIRDO++ is able to represent nominal geometries unseen during training within distribution. The reconstructions of test objects are close to ground truth, aside from some fine details at the edges. Our model can also predict the unseen objects' dynamics based on their nominal shape. Again, the observations of the unseen objects include occlusions at the tip. The results show our model's generalization capability, where it can predict unseen objects reasonably well. By adding a training dataset with 2 scraping trajectories on the walk, we perform state estimation and predictions. Our model provides high-fidelity dense geometry of deformable objects in high occlusion cases without a 3D model or configuration of the environment. However, due to the complex environment, it occasionally produced undesirable artifacts. This video shows the entire test results in walk scraping task. Our method can also be applied to rope-like object. We assume a scenario where a robot grasps the end of the bike chain. Here we train our model on 216 transitions inside a bounding box and tested on unseen 20 transitions. End effector orientations were fixed during bike chain manipulation because geometry changes are dominantly caused by transitions rather than rotation. This video shows that our model is able to predict and estimate both free space and in-contact chain geometry. The in-contact phase occurs when the arm moves sufficiently far down such that the chain lays on the table. Interestingly, we observed that bike chain demo shows better results on both state estimation and predictions than spatula demo. We hypothesize that this is because the action space dimension of bike chain is healthy one of the spatula, resulting in a simpler model to learn. In conclusion, VIRDO++ is a novel approach of learning deformable object dynamics conditioned on action, contact, and tactile feedback. We validate our state estimation and dynamics predictions using two types of objects and showed how our model can be generalized towards unseen objects and environments. Thank you.